Hello again from Digicore Things. So, as an overview, Europe Card Bus, or ECB, is a retro CPU bus standard from the late 1970s, early 1980s. The Minimalist Europe Card Bus, as I'm calling it, is a retro 8-bit CPU bus and PCB design standard that I decided to define and document. The purpose of which is to provide a modular platform for me to re-experience the fun of experimenting with the different 8-bit CPUs and the various video and peripheral devices that I grew up with in the late 1970s and early 1980s. My goal is that of a robust and modular design platform that would allow me to create interchangeable boards based on time-proven reliable bus connectors and modern low-cost prototype PCB manufacturing. In other words, a robust, flexible and low-cost way for me to recreate some of the early microprocessor circuits that I'd originally built using wire wrap methods back in the day. As evident from the name, it's based on a minimalist implementation of the original Europe Card Bus ECB standard. So a bit of background. A long time ago, back in the early 80s, I developed my first microprocessor system designs around the Motorola MC6809. I built these systems using Vero SquarePad Eurocard boards with wire wrap and DIN 41612 bus connectors. Back then, this approach was the optimal way of building homebrew microprocessor and digital circuits. In recent times, I've discovered some of my old wire wrap boards. These had been packed away in storage boxes for half a lifetime. This got me thinking about possibly recreating some of my old designs using modern PCBs instead. Here's a couple of examples. This is my 6809 CPU board, wire wrap, which was recently featured in a couple of videos I did on bringing this back to life. And here's another one. This is a MC6847 video display generator board that was populated with a row of 2114 static RAM chips, a total of 6K of RAM, and that as well was wire wrap on the same Eurocard grid boards and using the same DIN 41612 bus connector, which you'll note is a keyed connector and very reliable. So I considered my various retro boards and also the various peripheral chips that I had in storage. I also considered my original Eurocard based bus approach. I decided that instead of just recreating my existing wire wrap board designs onto fresh modern PCBs, I really should revisit the custom bus that I'd used and also ensure that I followed a nice modular and flexible approach. So it wasn't just a case of recreating some old wire wrap 8-bit designs onto PCBs. I really wanted to create a modular design standard that would allow me to experiment with different video display chips, different peripheral devices, and also different CPUs. To use a common idiom, I wanted to be able to mix and match. Of course, I'm aware of the more recent RC2014 retro modular design approach, but given my early experience using quality Eurocard boards with their professional and robust DIN 41612 connector-based bus solution, there are a number of significant aspects about RC2014 that did not appeal to me. What doesn't appeal to me about RC2014? Well, the use of the less than robust pin header strips as the basis of the bus backplane, that the bus connector is not keyed, which requires the RC2014 boards to have a cut-off corner design to help identify correct orientation, and hopefully not plugging the boards in backwards. That the original 39 or 40 pin header strip bus has evolved into a double row, requiring the added second layer of wider right angle headers, which makes board insertion even more fun. Of course, RC2014 does have some benefits. There's an existing range of available boards to play with, and the low cost of the pin headers as a bus solution. One thing that I did want was a low-cost solution. Looking at Mouser, for the current prices of the highly desirable DIN 41612 connectors, I discovered they were rather expensive, at around $7 or more per connector. But after a quick search of eBay and AliExpress, I discovered that very affordable connectors are indeed available, especially in the lower cost 64-pin ANC 2-row variant, as opposed to the full 96-pin ABC 3-row connectors. Here's a couple of those as an example. These are from AliExpress, and that's, as you can see on the back there, is a 2-row female vertical connector, and this one here is a male right angle connector. And you can see the screw holes, how they screw to the circuit board, and they're actually keyed so they only fit together one way. So this satisfies my low cost robust connector requirement. And sure, even a DIN 41612 connector sourced from AliExpress is a little more expensive than a 40-pin header strip. But spending $1 or $2 gets you a keyed, robust, easy to insert and industry proven bus connector solution. The small cost seems to me to be perfectly justifiable and a relatively trivial cost in the scheme of things. So the next step was to decide on an appropriate bus pinout standard to use. My old boards, which I'd created in the early 1980s, just used my own devised non-standard bus pinout. This was pretty common in those days. My Google research identified the Europe Card Bus, ECB, as the logical standout example DIN 41612 microprocessor bus pinout. Wikipedia tells me that the ECB was originally developed in the late 70s or early 1980s by a German company, Kontron. It originally utilised the same 64-pin row ANC DIN 41612 connectors and was also based on the standard 3U format 160mm by 100mm sized Eurocard PCBs. This is the same PCB standard and DIN connectors that I, and presumably many others around that time, were using for their new microprocessor-based bus designs. Google also told me that RetroBrew computers appeared to now be the current home of ECB, and that the current Europe Card Bus standard had since evolved into utilising the full 96-pin 3-row DIN connector. However, what I was looking for was more of a minimalist ECB requirement, simplified to provide a low-cost modular solution for the kind of hobbyist 8-bit microprocessor projects that I had in mind. Even some aspects of the original Kontron ECB 2-row design would seem unnecessary. For example, the Z80 specific interrupt and bus request daisy chaining. Therefore, I decided on a, let's just call it, minimalist ECB approach, intended to satisfy a couple of simple cost-saving features I wanted. I wanted to utilise only the lower cost 64-pin DIN 41612 Type C connectors, and I wanted to satisfy the 100mm square maximum board size for low-cost prototype PCB manufacturing. Limiting the board size to 100mm square should be fine with a modular approach, where the intent isn't to create a single board computer. In addition, although the intention is to use retro through-hole parts, board space savings can likely be made in areas like glue logic and buffers. So, for a modular bus system, the first thing we'll need is a backplane for connecting our boards together. RetroBrew computers have published Backplane 4 design, which fits into my desired low-cost 10x10cm format, as they describe it. Technically, I could just use this existing ECB backplane PCB design and instead populate it with cheaper 2-row ANC 64-pin connectors instead of the prescribed 96-pin 3-row connectors. But there are a few features that I would like to have that just utilising this existing Backplane 4 would not deliver. Firstly, I would like to include a 5th right-angle DIN connector. This would facilitate mounting a board horizontally for ease of access during hardware or software debugging, and also for prototype board development. In addition, the horizontal connector could also allow for extension of the backplane. I'm not happy with the existing 4-pin Molex disk drive power connector. For a 5V only system in the 2020s, I'd prefer perhaps a DC power connector, perhaps even a USB-C connector for the now common 5V USB power supplies. also a screw terminal for benchtop or any other desired power connection. And thirdly, for consistency and visual tidiness, I decided that I would first develop a standardised mechanical specification for a minimalist ECB board, or MECB. The specified standard board outline would then form the basis of all MECB boards that I developed for a tidy, consistent and attractive complete system solution. And if you consider that my desired backplane would also include a right angle DIN connector on one edge, then it can be seen that a backplane board can indeed also utilise the exact same mechanical outline as any other MECB board, simply that the backplane board will also carry a row of 4 vertical connectors. Okay, so the next consideration is the MEC board's simplified but flexible address decoding glue logic. As mentioned earlier, I wanted to be able to create MECB peripheral boards that implemented addressing flexibility. This is to allow a single board design to be utilised with different retro 8-bit CPU boards and with different memory maps. This would then support whatever 8-bit CPU-based design I might want to explore and experiment with. Another consideration is to ideally provide simplicity and consistency to the address decoding schematic, which could then be used as a template across different board designs. In addition, minimising the PCB board area required to implement the glue logic, whilst maintaining retro through-hole components. When reviewing my old-school designs from the early 80s, there were typically a small handful of 14-pin and 16-pin TTL packages featuring in each address map-specific address decoding glue logic. With this in mind, another important consideration is to reduce the signal load, hopefully avoiding the need for buffers to drive the bus. A single low-power CMOS input would clearly be preferable to the load presented by multiple TTL gate decoding glue logic inputs. The logical conclusion is to utilise a retro PLD device, which fortunately Microchip or Atmel still produce as the ATF16V8 and ATF22V10 and others. Some people may well disagree with this approach, but I believe this is the logical solution for achieving a flexible but still retro address decoding design. So in summary, here's some reasons why a simple PLD is a logical address decoding solution. Address decoding is about the simplest and most basic use for which you can use a PLD device. Designing your address decoding logic is as simple as writing the address decoding logic statement. Programming an ATF PLD chip is just as simple as programming an EEPROM. Many makers who are into retro microprocessors already have a TL866 programmer in their toolkit for burning EEPROMs. So basically minimal PCB space usage, minimal bus load, and most significantly full address decoding flexibility is achieved. The economical 20-pin retro dip packaged ATF16V8 appears to have all that is needed. This device has 18 pins available, 8 of which are I/O and 10 are inputs only. In simple mode, 2 pins are permanently configured as outputs. As the ECB bus utilises the memory request and I/O request approach of the Z80, i.e. a separate I/O address space, my thinking is that for my first design I'll utilise 15 pins of the ATF16V8 for inputs, allowing up to 3 pins to be used as chip select outputs. So in summary, the 5 most significant 64K address lines, A15 down to A11, would allow for memory decoding with 2K byte resolution. The 5 most significant I/O address lines, A7 down to A3, allowing for I/O decoding with 8 byte resolution. And finally 5 control lines, memory request, I/O request, read, write and clock would round out the 15 inputs. Where this isn't sufficient for the required decoding, then a board design could, of course, still implement some supplemental gates to complete the glue logic, while still maintaining a minimal chip count and still retaining some PLD-based address map flexibility. Alternatively, some control lines could be swapped out. For example, if read and write were not required in the address decoding logic, perhaps M1 on a Z80 system might be desired instead. By defining an initial ATF16V8 pin allocation assignment, this can then be included in an MECB standard board design KiCAD template to speed up the process of designing a new board. If sufficient PCB space is available, it's also worth ensuring that the space allocated for the ATF16V8 can optionally support a 20-pin zero insertion force socket to provide for ease of address decoding swap-outs. In this way, when using peripheral board to experiment with different system configurations, it'll be easy to just swap out the PLD for different memory map requirements. Of course, if you're building a more permanent system, then you could just utilise a regular 20-pin IC socket. With this in mind, I've included an ATF16V8 in the KiCAD template, also implementing a standardised PCB layout location with connector clearance to support a 20-pin zero insertion force socket. If not required, it can of course simply be relocated or even deleted from any new board design. So this brings us to our standardised mechanical specification for a Minimalist Europe Card Bus design. The design parameters were to satisfy the 100mm square maximum board size for low-cost prototype PCB manufacturing, to also utilise the lower-cost 64-pin DIN 41612 Type-C connectors for cost saving, and to ensure the DIN connectors can be easily centred across the board width, grid-aligned. I also provide two standardised corner holes on the edge opposing the right-angle DIN connector to allow for attachment of card handles to ease board insertion and extraction, or for board mounting. And I also provide an additional two standard corner mounting holes on the edge with the right-angle DIN connector to provide a full set of 4 corner holes to allow for standalone board mounting. I also wanted to standardise the PCB corner rounding for sharp corner removal consistency across all boards and for visual tidiness. A few design notes. The PCB layout is designed utilising a 0.127mm or 5mm grid setting. The board size is 99.822mm, which represents the greatest even multiple of 0.127mm. That is, multiples of 0.254mm or 10mm that will fit within the desired maximum 100mm board dimension. Standard M3 size mounting holes were chosen. An additional 2 mid-edge located mounting holes are specified for the backplane board only to provide additional mechanical support. For reference, the DIN 41612 connectors can utilise standard M2.5 mounting bolts, 8mm in length for straight connectors and 10mm in length for the right angle connectors. And finally, this is implemented as a KiCAD template to assist with simplifying the creation of each new MECB board design. And there's a diagram of the resulting standardised board mechanical specification. So next up, we'll be designing some boards, of which I'm already well into my first 4 or 5 boards. But until then, that's it. Thanks for watching.